Okay, so the video for today we're going to be going through the disk method, which is one of the methods in which you can find volumes of lines or segments or anything being when they're rotated around a axis, be it the x or y axis or a line. So first, just to explain real quick, like what the disk method is, in case you still don't get it. It's basically just a method of finding the volume of something when you rotate it around an axis. So say we had the line right here, y equals negative x plus 1. So you can graph out that line, and it looks like what I have here with, the y-intercept at 0, 1, and the x-intercept at 1, 0. And you want to take that line, and say the problem tells you to rotate that line around the x-axis and to find the volume of the solid formed by that. So you're going to basically look at that red arrow and say, okay, so I'm rotating this whole entire line around the x-axis. So the whole thing is going to get rotated. And what you're going to do is you're going to end up with a cone like this cone on the right. Kind of envision that in your head. That's what you're doing. So to find the volume of this cone, obviously for an easy shape like a cone, you could just use the radius. And the radius here is going to be a 1 because that's this right here. That's that 1. And you could obviously just use that and say, okay, well, the volume of a cone is 1/3 pi r squared h. And then you could plug in 1 for the radius and get the volume as pi over 3. But you can also do this by way of the disk method, which is using integrals to find the full volume. So basically what you're doing with the disk method is you're taking this cone and you're slicing it a bunch of times, really small, into a bunch of little circles. So like say you take this end circle here, you'd remove it, you get that one really paper thin circle. And then what you're doing is you're taking the integral of the area of each of those circles, so the radius squared, pi times the radius squared of each of those circles. And then if you take, the integral, you're summing up all those areas, and the sum of all those areas is going to give you the area or the volume of the cone itself. So that's basically the theme, the stuff behind it. Whoa. Sorry, I'm still getting used to the new video thing, so if a lot of things are moving, not my fault. Okay, so first I'm just going to go through, these are kind of the steps that I go through in my head when I think about doing the disk method. So the first step is always to graph. Whatever equation they give you, just graph it. Then they're going to tell you what you're revolving it around, so decide what axis or what line they're revolving it around and kind of envision that in your head. So once you graph it, revolve it around whatever they tell you to revolve it around, envision what it looks like in your head, and then the second step is to cut your disks perpendicular to the axis of rotation. So like for that example we just had with that line where it was going around a cone, we rotated around the x-axis, but we wanted to cut our disks perpendicular to that axis, so in the y direction like that. The third thing, make sure you don't have to subtract any inner empty space, so with the more complicated expressions, when it's not just a sector right up against the axis of rotation, you're going to have to subtract out some empty space when you envision it in your head, so you'll have to do that. Next, you're going to define everything, including the bounds of the integral and any variables inside the integral in terms of the axis that you're rotating it around. So whatever axis it was that they told you. And then the fifth step, obviously, you're just going to evaluate the integral and get your volume. Oops. So, let's start with an example. So this example, I have them all graphed already because that would just take too long and I don't want this to be too long. But for this first example here, so say they gave you the equation y equals the square root of 9 minus x squared, and they told you to revolve that around the x-axis. Now, you know that this is part of the graph of a circle, because if you squared both sides, then you'd get x squared plus y squared equals 9, so it's a circle of radius 3. But you only have the section that's in this quadrant, and they're the first quadrant, and so they're telling you to revolve it around the x-axis, so you're going to get a hemisphere when you rotate it around, but you want to find the volume using an integral. So, first step is to graph, and we've done that. Second step, we decided they told you what axis you're rotating around, so we're going to cut disks perpendicular to that axis. So if we're rotating around the x, we want to cut disks in the y direction like that. And sometimes it's helpful to just draw some in so you remember what axis you're doing. Then you take the volume equals pi. You're always going to have that pi out in front there because you're taking the area of circles. So you're going to have a pi, but since it's a constant, you can move it out to the front of the integral. So you have v equals pi times the integral of the radius of one of the discs that you're cutting. So initially looking at it, you might be like, oh, well, the radius is just going to be 3. Well, it's not always going to be 3, because as you go along that line, the radius is actually changing. So, like constantly, because the value of the x value is changing. So, you know that y value that you want, that upper y value along this line here, is going to be given by the y. So just the y value of whatever's on that line, minus 0, because the lower part of that radius is always going to be 0 here along the axis. And that will give you the radius of your circle at any given point in time. Squared, because the radius, or the area of a circle is pi r squared, and then since you're cutting your disc perpendicular to the x-axis, it's a dx. So you've done that. The first 2 steps. Third step is to see if you have to subtract anything out. For this one you don't, because it's just a simple example. So then fourth step is to define everything in terms of the axis that you're doing it to. So you're going to take your bounds, and your bounds are going to be from, on the x-axis, since it's a dx, so it's going to be 0 to 3, and then you're going to change your y into terms of x. So in your y in terms of x, you already have it solved here, so the y is equal to 9 minus x squared to the 1/2. That whole thing squared, since it's y squared and dx. And now you have everything in terms of x, including your bounds and what's inside. So all you have to do is evaluate the integral. You get pi times 0, the integral from 0 to 3 of 9 minus x squared dx. Pi times, and then you evaluate the integral, that's 9x over, 9x over nothing, just 9x minus x to the third over 3, from 3 to 0. Evaluate that out, you get pi times 27 minus 9 minus 0. So that is, well, that's about, sorry, cut out there. So that is 18 pi as your volume. And for this one, it's also a simple integral, so you could have done this with the volume formula for a sphere, which is 4/3 pi r cubed. 4/3 pi times 3 cubed would give you 36 pi. And then since you're only doing half of this sphere, 36 pi over 2 would give you the 18 pi that you just got. Okay, so next we're going to do a little bit more complicated example where you have to end up using that third step, but make sure you don't have to subtract any empty space. So this one, when you have one like this, first thing you do is graph. Okay, so we got the graphs. I'm going to, to make it easier, I'm calling this upper line here y1 and this one y2. So at this point in time, the graphs, they look like that, where the x to the 5th is under the x squared. So what you're doing is they tell you to rotate this entire little sector around the x-axis. So you're not rotating the lines themselves separately this time, you're rotating this whole little area in here. That whole thing around the x-axis. So that's going to give you a kind of cone-looking thing, except there's that hollow space in the middle that's caused by this right here. So like that's going to be hollow, so you're going to have to end up subtracting that out. So take it from the top, you graph, and then you set up your integral when you divide. So you're cutting your disc perpendicular to the x-axis because that's where you're rotating around, so you're going to cut them like that. So v equals pi times the integral from, define in terms of y. So this point right here is going to be a 1, 1, right? Because that's where they intersect. Because both, 1, 1 is a point that's on both of those graphs. So you're going to take the integral from 0 to 1. Then after that, you're going to want to take the outer volume minus the inner volume. So you want to take what it would be if that space were filled in minus the space that you know is empty. So that upper line right there, the y1 is on top of the y2. So first, to take the outer volume, you would do the y1 minus 0 squared dx. And that would be, say you're taking the entire volume if even this little space here was filled in. Then you're adding in that third step there where you subtract. Sorry, I have to go into the next line here, but you should write it all in one line when you're doing it. You have to subtract the inner volume, which is the empty space that I was just shading right here. So you have to do the integral from 0 to 1 still, because it's in the same place, that's a 0. And then you just take the y2 minus 0 squared dx. And I know it probably seems easier to just do it all in one integral and do y1 squared minus y2 squared, and you're going to get the same result, but Glennon wants us to split them up because it gets easier once you get to more complicated ones. So, then you have your integral all set up, so you're going to redefine the y's in terms of x's, because you need to define everything in terms of the derivative you're taking. So y1 is equal to x squared, plug that in, squared dx, minus pi times the integral from 0 to 1, and then y2 is equal to x to the 5th squared dx. So then you simplify those, pi times integral from 0 to 1 of x to the 4th dx, minus integral from 0 to 1 of x to the 10th dx. Evaluate those integrals, x to the 5th over 5 from 1 to 0, minus pi times, this is a mess, I'm sorry, but x to the 11th over 11 from 1 to 0, and then when you evaluate that out, well, you'd get pi times 1/5 minus 1/11, so 6 pi over 55, I believe, is the answer there. Okay, so we'll go through like 2 or 3 or however many I have here, more examples. If I can figure out how to get to them. Okay, there we go. Okay, so this is one where you're not rotating around the y or the x-axis, but rather they're giving you a line to rotate around. So first step still is graph, but I wanted to leave this one ungraphed for now because I wanted to show real quick. So one like this, it's a little more complicated graphing wise, even though it's still not really complicated, but just in case. So what you want to do first is solve for their point of intersection so that you know kind of where the area that you're going to be rotating is going to go. So, just set them, typical solving equations, set them equal to each other, 2x squared minus 4x equals 0. Factor out of 2x, x minus 2. So then x equals 0 and 2. So then you know that those two graphs are going to intersect where x equals 0 and x equals 2. So plug in a 0, and that's a 0, 0. And plug in a 2. That's a 0, that's a 4, 2, right? Yeah, 4, 2, or 2, 4, excuse me. So you're going to have like something like that, 2, 4. And so you know y equals x squared is just a basic parabola. It's going to look like that. And y equals 4x minus x squared is also a parabola, but it's down facing. If you do out the completing the square, it's going to probably, I think, something like that, yeah. And obviously graph these a little more carefully when you're on the test, but you know that these 2 points are your points of intersection, so you're going to be rotating this area around the line y equals 6. So they give you the line y equals 6 as the thing you're rotating around, so you're rotating it like that. Y equals 6 is a horizontal line, so it's still going to be dx, so you're still going to be cutting your discs perpendicular, and you're going to do the integral pretty much the same way. So, but this is one where you need to subtract too, so be aware of that. So your volume, you're gonna set up like normal. So you're always gonna go top to bottom, no matter like where your area that you're rotating is, because it's just easiest to think that way, I think. So v equals pi times the integral from 0 to 2, because those are your x values, and you're doing a dx, because that's where you cut your slices. And you're rotating around y equals 6, so you're going to start, your radii are going to start, if you're taking the outer ones, at 6. So that's going to be a y value of 6 minus the y value of the outer line there. The outer line is the green line. So you want to subtract that y value from the 6. So that's an x squared, because that's your radius, d